Welcome to the Anritsu presentation on how to perform broadband 220 GHz VNA measurements. This is part 2 of the 3-part series. For part 2, we'll go over some of the choices that we have when performing broadband on-wafer calibration measurements. We'll discuss some of the choices and options that are available in configuring the system, and then review measurement best practices for maintaining calibration over a period of time. So before talking about the full probe calibration process and options that we have, I thought it'd be first good to discuss the power calibration aspect of a broadband system. Now, typically what you would be getting from a broadband system is a factory power calibration at the millimeter wave module test port, and that is what we do with the 220 GHz system. So there is a factory power calibration at the module plane. And for many cases, that should be adequate enough for a number of uses, especially when you're adding the probe tip directly to the module, since you don't have losses from RF cables being applied. And so that should be a reasonable place to start. But let's say after a period of time, you may want to update the power calibration. And so you can do that by using power sensors. And so what we would do is add our adapters to the module so that you can attach the power sensors for calibrations. So that would be both coax and waveguide sensors going up to 220 gigahertz. So you would have a coaxial adapter going up to 110, 125, and then add the waveguide adapters to add your waveguide power sensors. Then what that results in is, of course, you have shifted your power calibration plane to the end of your adapters, and what you now want to do is add your probe in order to make on-wafer measurements. And so you would take the S2P file of the adapter and de-embed the adapter, and then connect your probe, and with the S2P file of the probe, that would be used to embed the probe, and now you have shifted the power calibration plane from the power sensor to the end of the probe tip. And of course, the adapters that are provided with the system come with the S2P files as well as the probes. And so that process is pretty straightforward using the embedding, de-embedding tools within the VNA. So now we want to start taking a look at the calibration choices that we have for on-wafer measurements. This would apply for any on-wafer measurements, so whether it's 70 gigahertz or 110 or 220, some of these aspects will still apply. And one that many are already familiar with are the SOLT, or short open load through calibration. And these are commonly used up to 40 and 70 gigahertz, and they need well-defined standards, and therefore usually are not used above 70 gigahertz because of the drop-off in performance. So for on-wafer measurements up to 110 and higher, SOLT will usually not be used. And then others that are often available on VNAs are the banded types of measurements. So SSLT, SSST are examples of that, where there's multiple shorts, offset shorts, and because of the offset short definitions of the standards, they are considered to be more banded types of measurements. So they're more popular in waveguide VNA measurements. The SOLR is similar to the SOLT, except that the through may not be well defined or available, at least a good through. And so you would just use a reciprocal through and get your calibration coefficients through that process. There's a slight degradation in accuracy because it's taking some assumptions, but if that's all you have, then that would be a way to approach the situation where you don't have well-defined throughs. So then we get into the other group of calibrations that are often used in on-wafer situations, and there's different reasons for using the different types. Starting off with TRL, LRL, and multi-line LRL. The use of lines are what define the accuracy of the calibration, and so it's going to be a fairly good alternative to having well-defined standards, because as long as you have a good connection to a line that represents the characteristic impedance of the media, then you will usually end up with some fairly good results. LRM is similar to LRL, except instead of just using lines, you would use a match for one of your lines. And so the TRL and LRL are often sometimes considered band limited because of the multiple lines that you might need to use in order to get down to the lower frequencies. And sometimes there's going to be a real estate issue on the substrate to have very long lines in order to get down to low frequencies. So the LRM is a good alternative to that in order to get to the lower frequencies. And then you have options to the LRM called different names, such as ALRM or LRRM, and that's where you incorporate load models and more information like multiple reflects in order to further improve on the performance. So the ALRM and LRRM are also quite often used for measurements on wafer into the millimeter wave ranges. So this is another way to look at the different choices that we have in calibration algorithms, and it might help provide a little bit more information on when you would want to switch from one to the other. And what we can start doing is just summarize the fact that the calibration standards are going to be required to be fairly accurately defined, and so based on that, that's when you will start to choose one method over another. So again, going back to the SOLT method, that requires active definition of equivalent impedances of the open, short, and load standards, and it provides a precise, it requires a precise model of the through standard across the entire frequency range of the measurement. So this can be, very challenging, especially as we get up into the millimeter and sub-millimeter wave frequencies, and that's again why this method is typically limited to 40 to 70 gigahertz range. So the LRM and TRL, have advantages in that they do not require the reflex standards to be fully known, and they don't need to be fully known, across the entire frequency range. So we only need to measure the open and the short standards, and we only need to predict the phase characteristics within the plus or minus 45 degrees of the phase. And so this is relatively easy to do, and is why these types of methods are often popular for on-wafer calibration. So in terms of the multi-line TRL, these also use through standards and reflex standard, which can be either an open or a short. The difference is that the multi-line TRL, we use several different transmission lines of different lengths. And so what's unique about multi-line TRL is that it doesn't require an electrical model of the standards that we use. We only need to know the difference in the physical or electrical lengths between the standard, the through standard, and the line standard. So the through standards sets are reference 0, or the starting point for the multi-line TRL, and then every next line that we measure are defined only as the difference in their electrical or physical length to this reference point, and that defines our delta L. And also the starting point through the probe to probe distance does not necessarily need to be known. So we can start with any arbitrary position, which is typically about 150 microns. So that gives us another way to look at these options that we have in performing calibrations on wafer over a very wide frequency range. So this slide gives us another perspective on the challenges of calibrating probes. So when we think about calibration of the broadband system by touching down on cal substrate standards, we now start to think about the fact that those standards reside in, let's say, a calibration substrate, and that calibration substrate may not accurately reproduce where the DUT is located. So the environment of the DUT is quite different than the environment of calibration standards. And so this brings up many challenges, and that is why there's becoming an interest in not only performing these calibrations on calibration substrates, but also to add calibration standards on the DUT wafer so that we can start to calibrate within the environment that the DUT is located. And this also is starting to show us that the location of the DUT can be embedded deep within the wafer, and we therefore need to start thinking about de-embedding techniques, finding ways where we can move our calibration plane to the actual input of the DUT and not include the long transmission path that the signal must go through in order to reach the DUT. So again, these are some of the challenges that are starting to surface, And as we go into higher frequencies, we want to consider these aspects as well as some others that we'll start to get into now. So now we can start to look a little bit closer at the actual calibration standards that are located on calibration substrates. And when designing the coplanar calibration standards for millimeter wave frequencies, it's important to minimize possible coupling of the electromagnetic energy into the higher order propagation modes. That these can be supported by the calibration structures or the calibration substrate. So besides the thickness of the substrate dielectric material, the design and layout of the standards should be optimized for different criteria. For instance, things like minimal possible impact on the neighboring elements, maximum acceptable distance to the substrate edges, and then location of transmission lines in homogeneous environment. So you want to be cognizant, of these of the environment where these long transmission lines reside. So these recommendations have been developed by the European Metrological and Industrial Research Project, PlanarCal, which was led by PTB Germany, and they're also suggested in the guidelines for the design of calibration substrates, so including the suppression of parasitic modes for frequencies up to including 325 gigahertz. So these recommendations were addressed in the MPI calibration substrate, and it's what is recommended for the 220 gigahertz system. Some characteristics of the new calibration substrates were reported in the RFTAG 94th conference. Here we have a 3D electromagnetic simulation. It shows how optimization of the layout of calibration substrate standards can reduce possible propagation of higher order modes in the calibration environment. Both of the long transmission lines are at the same simulation conditions and color scale. This is a worst case scenario observed when measuring the longest transmission line. The RF probes are hidden in this picture. So the calibration substrate on the left with the sparsely populated layout shows significantly less coupling of the test element with the neighborhood environment and the smaller magnitude of the higher order modes propagating in the substrate. The substrate section on the right shows how locating the transmission line close to the edge of the substrate and close to the other standards can result in an increase in propagation of higher order modes. And so here's another simulation of some of the boundary effects when propagating these higher frequencies on calibration substrates. So when the calibration substrate boundary conditions are not matched properly, then the higher order modes may start propagating in the calibration environment. And so the left-hand picture demonstrates that type of situation. The calibration substrate is resting on metal, on a metal chuck, and as a result, the fields are corrupt. So this situation is critical for any calibration method. We have to make sure that the measurement of all calibration standards are conducted at a single quasi-TEM propagation mode. So the right-hand picture is using a ceramic jug, and it demonstrates this condition. So such an optimized condition can be achieved if the system auxiliary chucks are thick and are made of ceramic. The chuck dielectric constant has to be matched with the dielectric constant of the calibration substrate. So some investigation results for the ceramic chuck were presented at the RFTAG Fall Conference in 2008, and at that time the experiment covered the frequencies up to 110 gigahertz. So later, the best practice guide for planar S-parameter measurements using vector network analyzers recommended by the Planar Cal Consortium extended the results for higher frequency bands. Small compact millimeter wave modules are helpful in the choice of installation options. An additional point of interest in instrumentation installation is the use of magnetic base cable stress relief supports for the system RF and control cable interface. It not only reduces phase variations due to cable movement, it also removes the mechanical stress from the module interface and thus protects the probe contact. This is essential for repeatable and consistent data. Another helpful aid is the use of a digital micrometer integrated at the x-axis of the RF positioner. This enables easy and quick adjustment of the probe-to-probe distance with 1 micron accuracy and repeatability. It is extremely helpful when the operator needs to calibrate the system using the multi-line TRL approach. This concludes part 2 of the 3-part series on performing broadband measurements up to 220 GHz using the VectorStar broadband system. Please continue to part 3, where we'll discuss more detailed aspects of calibration accuracy and provide some examples of on-wafer measurements and calibration results. Thank you.